Welcome to lesson 4.1, day 2. We're going to learn about critical points. First of all, we have a little theorem 2 in your book. It doesn't really matter what it's numbered, but it says that if there is a local max or min, and if it has a derivative at a point, then the derivative must be 0 at that local min or max value. Of course, we already knew that, because remember, when you have a maximum or a minimum, you have a horizontal tangent, which means your slope equals 0. And since slope is the derivative, tangent slope is the derivative, we already knew that the derivative would equal 0. So let's take a look then at what critical points mean. And this is, these are very important to know, and you're asked to do this a lot in all of calculus. So we've come to a critical section here as well. A point where the derivative is 0 or the derivative doesn't exist is called a critical point. All right, and these are points we check to find a function's extreme values, maxes or mins. All right, we check the two critical points, the two places, where we could have critical points, and then we also check endpoints. And those are opportunities, we'll call them, to have extrema. Not all critical points and endpoints are extrema, but all extrema, all maxes and mins, are either critical points or endpoints. This is an important distinction. If you didn't understand what I just said, read your book or listen to me say it again. All right, we're going to do 3 examples, finding extreme values analytically. And you might say, analytically, well, you gave me a graph, so why can't I do it graphically? Well, we're going to kind of mix it up together, because in calculus, you're supposed to learn all of these facts 4 different ways: analytically, graphically, numerically, and verbally. So you should be able to describe any problem in any of those 4 ways. So we're going to mix it up. This problem, unfortunately, is not on your assignment, but it is from your book. Okay, so the derivative of this function is 3/5 x to the negative 2/5. Which means, if I rewrite this, it's 3/5, and we have a negative 2/5. So power 2 root 5. Okay, so what that equation, or what that expression, derivative function, tells me is that x cannot equal 0, right? Because the derivative does not exist at 0. Now, is there any place, and we're going to go through this, 3 different areas. Is there any place that the derivative equals 0? No. There are no places the derivative equals 0. You can't make that function equal 0. Is there anywhere that the derivative does not exist? And that is yes, at x equals 1. And then our third place to look at points is the endpoints. And we really only have one endpoint, because this function is defined from -2, not including -2, to x equals 3. So endpoints we're going to look at are x equals 3. All right, I made a little chart here to make this easier. We have a critical point at x equals 1. The derivative does not exist. Okay, and we have an endpoint at x equals 3. And this is the derivative. This is because it's an endpoint. We're putting that in there. All right, so let's look at whether these are maxes or mins. We're going to learn other ways to figure out whether it's a max or min. So right now, we're just going to look at our graph to figure it out. And like I said, we will learn other ways to figure out whether it's a max or min. There's a second derivative test and some other things. So anyway, at x equals 1, there is not a maximum or a minimum, okay, at either one. All right, this is an example where you have a critical point that is not an extrema. It's a very important distinction to make. All right, and then we also just want to know the function value. Remember, our function is x to the 3/5. So if we plug a 1 in there, we just get a 1. All right, the endpoint is actually, if we look at the graph, the endpoint is a maximum. All the points around it are less than the function value at x equals 3. And the function value at x equals 3 is just 3 to the 3/5. You can write that as a decimal if you want, but I wouldn't waste my time. Okay, so, all right, next example. We're going to find the extreme values of this function and where they occur. So let's take the derivative. I'm going to rewrite this. This is 1 minus x squared. And the exponent on this is negative 1/3. All right, so negative 1/3 is our exponent, and now we're going to take the derivative. I'm not talking because you know how to take derivatives. All right, we just need to clean this up a little bit. This is our derivative function. It might be helpful to rewrite this one more time just so we can set everything equal to 0. And that would be a 2x on the top, a 3 on the bottom, 1 minus x squared in the bottom, and we raise that to the, well, we take the cubed root of it, and then raise it to the 4th power. Okay, don't forget that in fact, this is what we're doing in Algebra 2. Rational exponents, it's power over root. So don't forget that, power over root. Now let's take a look at our scenarios for critical points and endpoints. The first one is, does the derivative equal 0 and where? This would be wherever 2x equals 0. So therefore, we have a critical point at x equals 0. Cool. Do we have any place where the derivative does not exist? Well, anywhere this inside the cubed root equals 0, that'll give us a 0 in the denominator, right? So let's take 1 minus x squared and set that equal to 0. Doing a little fancy algebra, we're going to see that x could equal plus or minus 1. Those are 2 critical points. Now, are there any endpoints? They didn't give us a domain for this, so we assume it's all real numbers from negative infinity to positive infinity. So there are no endpoints. Okay, we have none. All right, let's take the same chart that we did before and fill it out for our values that we have for critical points. X equals 0. We have the derivative is 0 at that point. We have 2 other ones, x equals 1 and x equals negative 1. The derivative doesn't exist at those 2 points. All right, is that a maximum or min? We're going to look at the graph for this. We have a local min at x equals 0. We have no max or min at x equals 1 and negative 1. In fact, we have asymptotes there. So we don't have a maximum or a minimum there. All right, the derivative value the function value at x equals 1. It doesn't exist for these 2 because they're vertical asymptotes. And then the function value, if you put a 0 into your function, remember your function is 1 over the cubed root of 1 minus x squared. All right, so if you put a 0 in there, you get 1 over 1. All right, so again, maximum and minimum we're determining from the graph. Okay? Last but not least, we always have to have a little piecewise function. I've also graphed that one for us. Let's take the derivative. The derivative of this is 2 minus 2x. All right, so let's look at our 3 scenarios. Does the derivative equal 0? Well, not less than 0, it doesn't equal 0. What about 2 minus 2x equals 0? Bet we can make that equal 0. So therefore, with a little more fancy algebra, we come up with x equals 1, positive 1, correct? All right, and then is there any place that the derivative doesn't exist? Well, just looking at the graph, and actually if you set these equal to each other, the two derivatives equal to each other at x equals 0, you will see that the left-hand derivative does not equal the right-hand derivative. Or you could say this is a corner. All right, so the derivative doesn't exist at x equals 0. What about endpoints? Just like the last problem, there are no endpoints. By the way, the last problem I think is on your homework assignment. I don't think this one is. Sorry. But you can figure out your other problems because you will have done this one. All right, let's fill in our little table. X equals 0, x equals 1. At x equals 0, the derivative does not exist. At x equals 1, the derivative is 0. Okay, is this a maximum or minimum? All right, we actually have a local minimum at x equals 0. Local min, you could specify a local because it's not your absolute min. And the function value when x equals 0 is 3, right? Because we use this part of the function. So at x equals 0 equals 3. All right, so that's a local min. All right, at x equals 1, we have a local max, right? According to our graph. And when we plug that into the equation, we get 4. And we would use the equation greater than 0 again to get 4. All right, so again, these are our examples. Have a great Section 4.1 derivative day.